Log on, tune in, find out. Another good idea from Cambridge.
Thanks, Gideon, and thanks for coming. I'll talk maybe more generally about epsilon-nets. So actually, the main new things I want to mention are mostly very short observations. And this I could have done very quickly, but the problem has quite a bit of history. So I thought I'll tell you more about epsilon-nets in general. And anyway, we have to somehow kill the hour allocated to this lecture. So I'll tell you about epsilon-nets. I think it's interesting. And let me start with, and please feel free to ask me anything anytime during the lecture. So let me start with some motivating question. And this will be just some examples of something more general that we'll talk later, but I think it's nice. And this is the following. So what is the minimum f, which is some function of n and epsilon? So we think about n as a large number maybe, and epsilon is a small positive real, such that, for every set of x of points in the plane, finite set of n points, there exists a subset y in x, which we will call later innate, and this y is of cardinality at most fn epsilon, with the following property, so that for every triangle, and again that's just an example, that's okay, so for every triangle T in R2 which contains a lot of the points of x, it must contain at least one point of y. So with a T intersection x at least epsilon n, we must have a T intersection y is not empty. So let's see. I suppose. Okay, so just to make sure that we understand it, so we have these many points in the plane, and what we want is to pick a few of them. So this is x. We want to pick some of them, maybe not so many, or hopefully not so many, so that whenever we take any triangle in the plane that contains at least 4 points or something, then it will contain at least one of the points of y. And the somewhat surprising answer, if you haven't seen it before, is that that this f of n and epsilon is bounded by some constant 1 over epsilon, log of 1 over epsilon, and the important thing here is that it's independent of n. Independent of n. Right? That's an exclamation mark, but it's independent of n factorial as well. So it's independent of n. And this is somehow, if you try to prove it directly, it will be very easy to prove something like this with a log n multiplying it. And it's quite surprising that, that this is independent of n. And this is a special case of a result of Hausler and Welzel, but really of Vapnik and Chervonenkis. So let me talk a bit about that. So this is just one example, and I want to have a few definitions. So we first define what we mean by a range space. So X F is a range space. Really a hypergraph if X is just a set, is a it will be either finite or infinite, set of points. So, but this just means that we will call them points, or sometimes we call them objects. And F a family of subsets of X, which we call ranges. Of subsets of X, these are called ranges. So you can call them edges. It's really just a hypergraph. And A, so we have this range space. A subset of X is shattered. Okay, if every subset B of A, for every subset B of A, there exists some range F in F such that the intersection of F with A is exactly B, right? So we have this set of points, and for every subset of it that we choose, we have some range that intersects, say, exactly with this subset. So this is called a shattered set, and the Vapnik-Chervonenkis dimension of this range space will be the supremum cardinality of a shattered set. So I'm saying supremum because maybe it's not a maximum, it can be infinity if there are shattered sets of all sizes or an infinite shattered set. So VC for Vapnik and Chervonenkis, X if F will be the maximum cardinality of A, so let's write supremum, although we will be mostly interested in cases when where this is finite. So this is the supremum cardinality of a set A, so that A is shattered. And we can think about some examples. So here is a example. X could be the plane, and F would be lines. So the Vapnik-Chervonenkis of XF will be 2, right? If we have 2 points, then there is a line containing both, there is a line containing this, there is a line containing that, and there is a line containing none of them. And this is the maximum because if you have 3 points, either they are not on a line and then no line contain all 3 of them, or they are on a line and then no line contain 2 of them exactly. So this is very simple. Here is another example. X is RD, and F will be a half spaces. And then the VC dimension is equal to D plus 1. This is really Radon theorem. So D plus 1, if we take D plus 1 vertices of simplex, we can separate them by a half space in all possibilities. And if we have D plus 2, then Radon theorem, which is really simple linear algebra, tells us that there are 2 disjoint sets, so that the convex halves intersect, and therefore no half space can contain one of them without containing the other. We cannot separate them. Okay, so this D plus 1 may be a general example, somewhat general example. So let X be RD, fixed D, and F will be semi-algebraic sets of constant description complexity S. So by this I mean that we have some polynomial equalities and inequalities, and the total degree of all polynomials is not more than something like S. Then also the VC dimension is some finite number that depends on the dimension and on this description complexity. So that follows from results of Milnor and Tom or Warren about the sign patterns of sets of polynomials. So So these are several examples, and in fact I could have written as another example, the example I started with, where X is the set of all points in the plane, and the ranges are all triangles. Okay, so this is also, it has I don't know, maybe VC dimension 8 or something like this, but definitely bounded. So we need more definition. That's the notion of this epsilon net or strong epsilon net. We'll have weak nets as well. So let me write again a definition. So let's have XF is a range space, and A is subset of X. Now I want it to be finite. Then Y, a subset of X, is an epsilon net. So we also have some positive epsilon, positive small really. So this is an epsilon net for X. If every range that contains a lot of X contains at least one point of Y. So exactly in the example there with the triangles. So if for every f in f, so that f intersection, So I want it to be, I want Y to be a subset of A, of the finite set as I started with. Okay, so A is a subset of A. Y is a subset of A, is an epsilon net for A, if for every f in f, if f intersection A is at least epsilon A, then f intersects Y by at least one point. And maybe more generally, so let me define it as well. So A is subset of Y, a subset of A is an epsilon sample or epsilon approximation again for A. If we have something stronger, so for every range F, then really if we look at the fraction of points of A that F contains, and we look at the fraction of points of Y that F contains, then these two differ by less than epsilon. So really Y kind of approximates what is happening in the set A for every range. It's in some sort of an additive approximation. And of course, epsilon approximation is also epsilon net, right? Because if the difference, so if this one is at least epsilon, then this cannot be 0. And the converse is not true in general. So we can give some examples. And then there is this result of Vapnik and Chervonenkis that range spaces of finite sets in range spaces of finite VC dimension have small epsilon approximations. Okay? And the same, of course, holds for epsilon nets. Let's state both theorems. The theorem maybe. So this was in the 70s, maybe 71 or so. So what they proved is that if we have this range space, and the VC dimension of it is D, and A, a subset of X, is finite, then there is an epsilon approximation Y, and the size of Y is only some absolute constant, 10, say, d over epsilon square log of 1 over epsilon, and a similar theorem, so using similar ideas, this is due to Hauser and Welzel in the late 80s, and this is if x, f, a as before, x, a, d as before, then there is an epsilon net y for a, and the size is at most constant d over epsilon log of 1 over epsilon. But you see that in both cases it's something that is independent of the size of the set A. Right? So it is, and therefore, for example, what I said for triangles follows, right? Because the VC dimensions there is some constant, so so you just apply this result, and the proof of this, if you haven't seen it, it's really a beautiful probabilistic proof. Basically, you take a random set of that size, let's say for the result for epsilon net, you take a random set of this size, and it turns out that with high probability it is an epsilon net, only that if you try to compute the probability directly, it somehow will not work, and you will think that you need some log n factor, and then there is some trick. So so you have to define some auxiliary event to compute the probability of that event, and to use also some combinatorial statements that is known as a Sauer or Perez-Shelach lemma that says something about the structure of these spaces with small VC dimension. But anyway, this is the result, and
so the first theorem. So the first theorem implies the second one.
Well, only is that here there is epsilon square, and here there is epsilon. So really, if you don't care about the dependence on epsilon, then the first is stronger. But sometimes you care. Maybe. So we want to know, and in fact, I want to talk about how tight this is. So let me just okay. So some other.
I mean, 1 over epsilon squared is bigger than 1 over epsilon.
Right. So you have a bigger epsilon approximation, and it's right. Yeah. Yeah. So it's yeah, but it's good. Okay. And so please do the same and ask questions. If okay. So these epsilon nets are very useful in many areas, maybe mostly in discrete and computational geometry, also in computational learning, and also in combinatorics in general. There are many applications. Maybe I'll just mention some kind of toy application. Let me just say it without writing it. So looking, say, at the result of Wapnick-Chervonenkis, it tells you immediately that if you have a big set of points in the plane, and suppose I want to prepare some table, some data structure that will enable me quickly to decide, given a triangle, I want to approximate up to an additive error of an epsilon fraction of the total number of points. I want to decide how many of my points are inside the triangle. Okay? So I can just take an epsilon approximation. I can write it down as a table. It will be a constant size table for constant epsilon. And then when someone gives me a triangle, I just check how many of the points in this table that I prepared lie inside the triangle, and that gives me an approximation of how many of the total number of points are in the triangle. So I don't have to remember them. I can kind of compress the data, and still approximately I know a lot about it.
Is it easy to verify that?
So for its polynomial time, because of this Sauer's lemma, yes, the total number of ranges is polynomial, but and there are ways to de-randomize the probabilistic proof. But given a set, deciding if it's an epsilon approximation or an epsilon, then you would have to go over the ranges. But as I said, it's not so bad. So think about it as a pre-processing. So you do it. Yeah. Okay. So if this shows that that it is useful. The actual applications are more sophisticated and are often interesting. So so people want to know how tight this estimate is. So let's call this star, and they want to ask how tight is this star. Now, in all interesting, so usually I think about d as constant. So this is like constant 1 over epsilon, log of 1 over epsilon. And in all interesting cases, 1 over epsilon is a trivial lower bound, just because you can find usually 1 over epsilon pairwise disjoint ranges. And each of them will contain or may contain an epsilon fraction of your set, and in each of them, so let me just say that omega 1 over epsilon is essentially always, so let's write always, a lower bound. Well, almost always a lower bound. And what we want to know, is the log 1 over epsilon term needed, okay, for constant t. Okay, so for d equals 1, actually it is not needed. For d equals 1, the structure is very simple, and we understand it, and it is not needed. But for d equals 2, it is already sometimes needed. So they are abstract, and now we are talking about abstract range spaces. Let's see if I want to. Okay. So so that's a result of the Tach and Woginger. Maybe sometime around 90, and this is that for d equals 2, there are abstract, so not geometric, maybe, so abstract range spaces which require, okay, of VC dimension 2, that require nets of size omega. All the constants here are reasonable constants, so maybe 1/3 or something, 1 over epsilon, log of 1 over epsilon. And so there are several examples that one can give. One possibility, for example, which is maybe not the one in that paper, is to take a projective plane, a finite projective plane, and for each line in the projective plane, take a random subset of half the line. So this will have this property. If you don't want random subsets, just take all the subsets of at least half the points of the line for each line. Okay, no, you don't want to do that. So don't do that, sorry. Take take a random subset of each line. Yeah, you don't want to take many. Right. Okay, so this will have this property with high probability, but for the geometric cases, there were several examples. So let me list a few. So in geometric settings, it is known that sometimes there are nets of size linear in 1 over epsilon. So we don't need the extra log term. Okay. There are lots of results about special cases where there are linear epsilon-nets. So I'll list a few. So point objects and the half-space ranges in dimension 2 and 3 is an example. Also point objects and disks and pseudo-disks in the plane is also an example where there are linear. And there are also a few dual examples. So by dual I mean that objects are things like rectangles, and the ranges, for every point, you take all the rectangles that contain this point. Okay, so this is also geometric, and
but in those cases, a random subset will be not true, I suppose.
That's right, yeah. So in those cases, no, if you take a random subset, then you need the log term, right, yeah.
So
Yeah, so in all the cases in geometry where you need, where you know that the log is not needed, you have to be clever about constructing it, right?
So is there some sense in which you can say that for the random choice, 1 over epsilon log 1 over epsilon is tight?
Right,
You
yeah,
can come
yeah.
up
So
with, you
yeah.
certainly can come up with.
Yeah, so essentially essentially in every interesting example, if you do it randomly, then you would need the log term. Right. So it is, yeah. So it is. Now we talk about being more clever. So okay, so I won't use all of them, but for example, there is this result of Matuszek, Seidel, and Welzel. That for points in R2 or R3 and the half spaces, there are nets of size linear in 1 over epsilon. And as I said, similarly for disks and pseudo-disks, for some dual. So in fact, I won't list all of them, but starting in the late 80s, this paper is from 90, and starting from the late 80s until maybe a year ago, there are lots and lots of papers. So just put some initials. So maybe the first one is by Clarkson, and then there is one by Chazelle and Friedman, and there is this paper that I mentioned by Matuszek, Seidel, and Welzel. Yet another paper by Matuszek. So they all deal with some special cases where you try to prove that in some geometric settings you don't need this log term. Then more recently there was something by Clarkson and Varadarajan. Well, I'm just putting letters here. By Harpeled, Kaplan, Sharir, and Smolodinsky, and then Pirga and Ray, etc. So they all give some geometric examples where the log of 1 over epsilon is not needed, and somehow in many of these papers they say that they end by saying that the prevailing conjecture is that in all natural geometric situations in low dimension, so low VC dimension, there are linear epsilon-nets. So the log term is not needed, and there are some and there are some examples in which we know that this is true. Okay. So one thing that I want to show you is that that this is not the case. That indeed in actually in very many natural low-dimensional geometric situations, maybe in almost the most simple ones, then there are no linear epsilon-nets. So this is one new result, which will be very simple. So I'll show you the proof of that. So this is so this will be the following: that there exists a set or sets, but it's a family, but never. There exists a set X in the plane of size n that require nets, so epsilon nets of size A. Okay. Do it specifically. An epsilon net of size at least 1 over epsilon omega of 1 over epsilon. I should say what this means with respect to lines. Okay, so the objects are points, the ranges are lines. This is more or less the simplest or the very simple thing that we can think about, where omega grows but grows slowly. So omega is some version, so let's write inverse Ackermann, or some version of inverse Ackermann. So it's a function that grows to infinity very slowly when 1 over epsilon grows to infinity, which means that this is not linear. So this is one result. This a few months ago, but actually there is something newer, and that's due to Pach and Kardosh. And this is that, so maybe write in 2 steps. So there are x in R2 also of size n that require, that will be much stronger, that require epsilon net of size omega 1 over epsilon log log 1 over epsilon, so that's huge compared to inverse Ackermann, right? With respect now to something slightly more complicated, with respect to axis parallel rectangles. Okay, and in fact there are also examples that require 1 over epsilon log of 1 over epsilon, but this is slightly more difficult to describe, so that's some dual example in the plane where your set of objects will be some family of rectangles, and the ranges will correspond to points. For each point you will take all the rectangles that contain these points. Let me just say that there are also dual examples, requiring nets of size omega 1 over epsilon log of 1 over epsilon dual planar. So it's still something that can be described in the plane. It's a natural geometric example. So the first proof that, as I said, I'll tell you, is really very short, but it uses some sophisticated tool. These proofs are clever combinatorial results that are nice, but probably I'll not show them. They're also not very sophisticated, but maybe you need half an hour to describe the proof. The advantage of the first proof is that it works for weak epsilon nets as well. So let me tell you about, and it seems that this example do not, or at least we don't know. First mu works for weak nets as well. So let me tell you about what is a weak epsilon net. Okay, so this is again a definition. So we have this XF is a range space. A is a subset of x as before, finite. And now y, a subset of x. And note that this time I wrote x and not a deliberately, so it is not necessarily a subset of a. Subset of x is a weak epsilon net for x if again, if for every f in f,
Epsilon net for A?
for
Epsilon net.
a, yeah, okay, thanks. For a with respect to the ranges in f, if for every range f, if f intersects a by at least epsilon a, then f intersects y, so it's exactly as before, but y is not necessarily a subset of A. So we are allowed to choose things from outside A, and that gives us more freedom, and indeed in some cases there are weak nets when there are no usual or strong nets. And here is an example. So this is something that we proved some years ago with Baran Furedi and Kleitman. So there is a statement for every dimension, but let me just state it for the plane. Yes, so for every A in R2, finite, okay, finite, there is a weak epsilon net of size at most constant 1 over epsilon square, so again some function of epsilon, and this is now with respect, I didn't tell you what are the ranges, with respect to all convex sets. So the ranges are all the convex sets, okay? And note that the VC dimension of the set of all convex sets is trivially infinity, because you can take...
Erase the newer, so Pach-Tardosh doesn't apply to weak?
No, yeah, or at least it's not known, yeah. One of the constructions definitely cannot apply for weak, the other one is not known to apply for weak, so this is okay, and what I mentioned is that note VC dimension here is infinity, right? Because in fact it's even continuum, it's even not aleph naught, right? Because if you take all the points on a circle, then every subset here, you can take the convex hull of it, and this will be a convex set, and it intersects the circle exactly in this set. So this is a shattered set, and it's an infinite shattered set. And if the VC dimension is infinity, is big, then there are no small epsilon nets, right? Because whenever you take a set that is shattered, then you have to take almost all of it, 1 minus epsilon of it, to get an epsilon net, because every subset of it is, so this will be my whole space, and every subset of it, of epsilon of the points, will have to be captured. So weak nets give you more freedom, and therefore it will be harder to prove a lower bound for them. And let me also show you, tell you in passing very quickly why weak nets are useful. So our motivation was some question of Hadwiger and de Brunner, which is an extension of Halley's theorem, and this is just an application of weak nets. It's something like proved with Kleitman, answering. So there was a question of Hadwiger and de Brunner from the 50s, and it's an extension of Haley's theorem. It says that for every p, I'll state it in the plane, although it is true in every dimension. So for every p, which is at least 3, there exists a constant c that depends only on p, so that every, let's say, finite, doesn't really have to, let me say finite, finite family of convex sets in the plane, so that, it's a bit strange assumption, so any p of them contain 3 with non-empty intersection, okay. Any family like this can be pierced, I'll write, explain, can be pierced by C points. Okay, so you have this family of convex sets, maybe it looks like this. So this is kind of an uninteresting example, but it's an example anyway. So you see that here, whenever you choose 5 sets, then 3 of them come from this part. And therefore, indeed, you can pierce all the sets by choosing 3 points. So these 3 points will capture all the sets. Haley's theorem is the case p equals 3. If every 3 have a common intersection, then all of them have a common intersection. And this says this is an extension. And actually, for this, so a typical example, here is an example. Take x will be in R2, and x will be of size n, and f, the family, will be, or I don't know, maybe H will be all convex sets containing at least what? Well, strictly more, let's say, than 2 over p times n, 2 over p times n points of x. You see, these are convex sets, they are pretty big, and because they are big, whenever you have p of them, then the total measure of them in x, just by double counting, there is a point of x that belongs to 3 of them, because otherwise every point will be covered only twice, and we don't have enough space. Right, so this will satisfy this property, and because of this, if the question of Hadwiger and de Brunner is true, then there should be a finite set, a set of points whose cardinality is bounded by a function of p only, that intersects all of these. And if you think about it, this is exactly an epsilon-net for x with epsilon, which is equal to 2 over p. Right, so take epsilon equals 2 over p, and weak epsilon-net for x pierces all members of H. So at least for this example, it seems that what you need is exactly this weak epsilon-net. And somehow the main thing in the proof is to apply a frictional Haley and linear programming duality and some tricks to reduce the general case to this case, something like. Okay, so this is about weak nets, and then the statement about weak nets is also so just basically the same construction with one twist. We'll prove this lower bound for weak nets as well. So this will be also a theorem that there are finite planar Fs in R2 that require weakness, weak epsilon-nets of size omega 1 over epsilon, well, size, let's say, at least 1 over epsilon, this W inverse Ackermann of 1 over epsilon, and again with respect to lines. So with respect to all convex sets, I told you that the upper bound is 1 over epsilon squared. Even for that, until about a year and a half ago, there was no non-trivial lower bound. But then there is a bound more recently by Boris Buch, Matuszek, and Nivash, which is a lower bound of 1 over epsilon log of 1 over epsilon. But this is with respect to all convex sets. So this is a much weaker bound because it's inverse Ackermann, but it's with respect to lines. So we don't allow all convex sets, but we allow only lines, and still, maybe I'll mention also that if you think about points in the plane that are in convex position, then it is known that there are weak epsilon nets for them of size 1 over epsilon inverse Ackermann of 1 over epsilon. And there, this inverse Ackermann is tight. So there is both lower and upper bound. So at least inverse Ackermann indeed appears somehow with respect to this, some questions about these epsilon nets. Okay, so I want to tell you something about the proof and or the construction. As I said, the construction is very simple, but it uses...
The example from Buch, Nivash is very much not in context.
That's right, yeah. Which is similar, actually, those of you that have been in the lecture of Boris yesterday, although it seems that this was ages ago. Yeah. So it's something that they call stair convexity, where you take this grid with super increasing distances. So that trick is used there as well. But anyway. Okay, so I want to tell you something about proofs, and it will be very short, but it uses something deep, and what it uses is this density Hayes-Jewett theorem. To say something about this, so let k like this. Let it be 1, 2 up to k. So these are just the integers. And k to the d is k to the d. Okay, so we will look at all the sequences of all the vectors of length d in the d-dimensional Euclidean space, in which every coordinate is between 1 and k. And we want to define what is a combinatorial line. So a combinatorial line is a set of k points. So it will be L1 up to Lk, which is a subset of k to the d with, so I'll write the formula, but I'll show you an example. So with Li in coordinate j, okay, with maybe, right? So this is a combinatorial line. Is L, so there is some subset of the coordinates which is non-empty. This will be like the direction of this combinatorial line. And L, the ith line in coordinate j. So what I want it is to be J if I, no, coordinate J, we want it to be I if J belongs to I, and to be some C sub J if J does not belong to I. So probably those that have seen it before see that this is correct. So if it's correct, and those that haven't, then it makes no sense. So, but so this is just e.g. So it means that there are some coordinates that KB3. So there are some coordinates that start at 1 and then go to 2 and then go to 3. And all the other coordinates stay fixed. So maybe this one is 2, and this one is also 2, and this one is 3. So these are the rows are the 3 points of a combinatorial line. And you see that I here are the coordinates this, and so I is 1, 2, 3, 6, 8, maybe. Okay. So this is a line. Actually, it is a point on a geometric line also, right? It's a line that lies in this. Let's see how the example looks in dimension 2. In dimension 2, we would have maybe k equals 4. So this is a combinatorial line, right? And this is a combinatorial line, and this one is a combinatorial line, and that's it. This one is not, right? Because it's important that it's not, although maybe it will not be. Okay, what's this say? All right, and then what is this density Held-Hewitt theorem? So that's a result of Fürstenberg-Katzenelson. It just says that dense sets, even if they are pretty sparse, so they just have to be a little bit dense, then they must contain a combinatorial line. Okay, so yeah, maybe. So the theorem of Fürstenberg. Nelson. It is very easy for k equals 2, and they proved it first for k equals 3 in 89, then for the general case in 91. And it says that for every k in delta, there exists some dimension, which is a function of k in delta. So of course delta is positive, k is an integer. So that for every x, which is a subset of k to the d, d is bigger than d naught, and x is at least delta fraction of all points, contains, every x like this contains a combinatorial line. So the original proof uses some tools from ergodic theory, so it doesn't give any effective estimate for d naught, but we know that this d naught exists. But there is a subsequent proof by the first and most successful polymath project, and so that was in between January and March 2009, and some people here can tell you more about it, and this gives an effective bound. So d naught of k half, let's say, is of Ackermann type, is at most Ackermann of k. It's not exactly Ackermann, it's some version of it, but it's basically this. So this is some effective version. Now, why is this why does this give us what we want? So I just show you for a...
What about lower estimates?
Say that again?
What about lower estimates?
Yeah, it's very weak, a lower estimate. Yeah, they have something about lower estimates. I don't quite remember, but it's really completely ridiculous. So I won't even, yeah. Yeah, so that's, yeah, and it's interesting to understand the correct behavior here. But for k equals 2, we know it, but not, so that's basically Stirner's theorem. Yeah. All right, so why does this give us what we want? As I said, it's basically a very simple observation. So the whole thing, right, we had, I have to say these things, that we knew from those results of Pach and Woginger that there are abstract range spaces that require big epsilon-nets, and the whole thing is to decide if any of these examples can be embedded in a geometric situation. I wanted to say this sentence because I wanted to have the word embedding in my lecture. Because obviously this lecture has very little to do with embedding, but let's see.
You need to embed
anyway,
this
right,
word
yeah.
in there.
Yeah, but here we are really in a geometric situation. So note that, that now the k to the d, so every combinatorial line in this k to the d is really a line, is also a geometric line in RD. Only we are in very high dimension, right? But we are in RD. So if I take epsilon to be k over k to the d, then my epsilon net, suppose that I'm talking about epsilon net in very high dimension now. So my epsilon net, right, and d is bigger than this d of k and 1/2, then any epsilon net for, yeah, so this is x, for x with respect to lines must be of size at least half k to the d, right? Because the complement of it cannot contain a combinatorial line. And this half k to the d is equal to, so this is like k over 2 times 1 over epsilon. Right, and k, we can make it as big as we want, and it grows as this inverse Ackermann function of k to the d. I mean, the good thing about inverse Ackermann is that if it's inverse Ackermann of d or of k to the d, it's the same thing, right? So it doesn't really. So this would basically give us this this lower bound, and for weak nets, you okay, and but it's of very high dimension, right? So now you just project randomly. To a two-dimensional plane. So if you project randomly, then there are no coincidences, and every combinatorial line will be mapped on a line that does not contain any other points of any of the other lines. So really what you will be able to do in dimension 2 is what you have been able to do in dimension d as well. And therefore there also, now it will be in the plane, and there also you will need some big set. Okay, and that's basically it. For weak nets, you have to add an additional trick, so you have to look at this a little bit and to see that there are some other coincidences do not happen. So that's why I mentioned that, for example, it's important that this one is not a line, it's not a combinatorial line, and you can think and try to figure out why this is relevant. Let me just mention one open problem. So I just mention it. So open, or maybe I'll just state it as a conjecture, that there exists x in the plane, x equals n, that, or finite x, that require nets, epsilon net, of size really 1 over epsilon log of 1 over epsilon with respect to line. And I think it also should be true, so I have some specific example in mind, although I cannot prove anything about it. So just take an n by n cube, let's say, grid, usual grid, and take a random set of half the points here.
Random set of?
Yeah, just take a random set of half the points, half of this n to the 4 points, and then let epsilon be say n over 3 divided by n to the 4, namely I want to capture what's left. Every line will have here about half of the points it had before, and I want to be able to capture all the lines that have at least n over 3 points, and it seems to me that that you need in this example to take n cube log n points, that you cannot do better than taking about log n columns, right? But this I don't know, and let me finish here, and thank you for your patience.
Any questions? No questions? I have a question. What about the epsilon approximation? What are the best bounds that?
Right, so we know that the 1 over epsilon square term is needed. There is nothing about the log, I suppose. Right. Okay. Yeah, but that's also right. Yeah. Okay.
Other questions?
Yeah.
Thank you again.
Okay.